Hey everybody, today I'm going to teach you about Lewis dot diagrams, how to draw them, and what to use them for. Now, Lewis dot diagrams are ways to represent the bonds in molecules between atoms or polyatomic ions. They were named after the chemist Lewis Dot because they were his diagrams that he created. And, sorry, it seems that they were not created by someone named Lewis Dot, but actually a chemist named Gilbert Lewis. But the dots. And there are dots to represent electrons in them. So we're going to go over the steps to draw a Lewis dot diagram and then show you what it tells you about the shape of the molecule or that polyatomic ion. Is that okay? No, I'm not going to redo it. So I'm going to go through the 5 steps to drawing a Lewis dot diagram for high school students, and we'll look at 2 examples over here. The examples I'll work through is CH2O, which is called formaldehyde, and this NO2 with a 1- charge is actually called nitrite. It's an example of something called a polyatomic ion. Now the first step is going to be to figure out how many electrons you'll be working with to create your structure. So that means you're going to be counting up all the valence electrons from the atoms and then adjusting based on the charge on the overall thing. So here, if there's no charge listed, that is a molecule and there is no adjustment. But with a polyatomic ion, this entire thing carries this charge for 1-, and so it will have to be adjusted. You'll look at the valence electrons using a periodic table or this reference, and you'll see that on the reference that the carbon has 4, that there are 2 hydrogens, each with 1, and that the oxygen has 6, which gives us a total of 12 valence electrons to work with. In this case, the nitrogen has 5, there are 2 oxygens, each with 6, and we are going to adjust because of this charge by adding 1 extra electron. It's a negative charge, and so we will add electrons. And so with this, we'll have 18 electrons to work with. Our next step will be to determine which of these atoms is going to be in the middle that the others will be branching off from. And there are some rules about that it can never be hydrogen, and that if there is carbon present, that the carbon will be in the middle. Otherwise, it will be the least electronegative element. And without a chart that shows you electronegativity, remember that the most electronegative element is fluorine, and so the further away from fluorine, the more likely they will be the central atom. So in this first case, we have a carbon, and so it is going to be the central atom. with the 2 hydrogens and the oxygen around it. In this case, there's no hydrogen to worry about, there's no carbon, and the least electronegative element here is nitrogen. It's further away from fluorine, and so the nitrogen will be central. Our next step is going to be to connect these outer or peripheral atoms to the central atom with single bonds. Each single bond will be represented as a line, and that line, a single bond, recall, represents 2 electrons being shared between the atoms. Now in each of these, we've used up some electrons from our total that we said we had to work with. We had 12 to work with, and with each of these bonds, we've used up 2 electrons. We've used up 6, and so we have 6 electrons remaining. In this case, we started with 18, and we've used only 4, and so we have 14 electrons left. And that's important to know because we're still trying to make everything stable, and things are stable when they have 8 electrons connected to them, except for hydrogen, which is stable with only 2 electrons. So that means the hydrogen, as long as it just has 1 bond to it, will be stable. There should never be any extra dots or any extra electrons or any double bonds to a hydrogen. So our next step is to take those remaining electrons and to place them on the peripheral atoms first to see if we can make them stable. The oxygen here has 2 electrons connected to it right now because of the bond, and so we will need to put 6 electrons onto it. The hydrogens, as stated, these bonds represent 2 electrons, and so they have 2 electrons connected to them and are stable. With this, each of these oxygens has only 2 electrons connected to them right now, but they need 8 to be stable, and so we would put 6 on this one and 6 on this one. We'd have 2 electrons left, and we would put those on the nitrogen in the middle before we ran out of electrons. Our last step is going to be that we check all atoms for stability, which means a hydrogen would be stable, having 2 electrons connected to it. Everything else would be stable, having 8 electrons connected to them. So we're going to check and see if all of our atoms have that. And so here we see that the hydrogens are both stable, the oxygen is stable, but the carbon, having the 3 bonds to it, only has 6 electrons connected to it, and so it is not stable. If something is not stable, you can't just invent new electrons to make it stable, but what you would do is you could take a pair that were just dots before, that were non-bonding, and you can shift them and make them into a double or triple bond if you need to. And that's what we're going to do here. I'm going to redraw this diagram, but take those 2 dots and turn them into a double bond. And so you see now the hydrogen has a bond, which means it is connected to 2 electrons and it is stable. So is this one. The oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons connected to it, and so it is stable. The carbon now has 1, 2 from this bond, 3, 4, 5, 6, 7, 8, and so it is now stable. And this is the correct Lewis dot diagram for formaldehyde. We'll apply that same reasoning here. We can see that the oxygen has 1, 2 from this bond, 3, 4, 5, 6, 7, 8, and so it is stable. This oxygen has 1, 2 from the bond, 3, 4, 5, 6, 7, 8, and so it is stable. The nitrogen has 1, 2 from this bond, 3, 4 from this bond, 5, 6, and so it is not yet stable. We'll do the same thing. We'll take 2 electrons from one of the oxygens, and instead of just having them be dots, we'll put in a line to have them represent a double bond. Because these are both oxygens, it's arbitrary which one you choose at this point to make the double bond. And now when something is a polyatomic ion, you put brackets around the entire thing, and you put the charge on the outside. This does not have a charge and does not need brackets around it to indicate that. All right, so those were the basic steps and some examples for some typical high school level problems. Now, you're welcome to leave, but if you want to see how to do AP or college level problems, we'll look at some of those exceptions now. What will follow are some AP or college level exceptions or extra rules that apply to drawing correct Lewis dot diagrams, ways that the 5 steps that we just went over that you would learn in a typical high school class are going to lead you to incorrect or not completely correct answers. And so for that, we're going to look at 3 other examples. And the first of those examples will be something called sulfate, which is another polyatomic ion. It has a charge overall, and its formula is SO4. Another example is that we'll look at dichloroethene, which is C2Cl2H2. And last, we'll revisit the NO2 with the 1- from earlier, nitrite. If we were to follow the 5 steps for drawing the correct Lewis dot diagram for sulfite, it would look like this. In our diagram, we have the correct number of electrons represented. The sulfur supplies 6, 4 oxygens each supply 6, and a 2- charge means that we're going to add in 2 extra electrons. So you should have 32 electrons. With the 4 bonds, that means 8 electrons plus another 6, 6, 6, 6 gives us our total of 32 electrons. And so it would appear that this is a correct Lewis dot diagram, especially because with the 4 bonds connected to it, the sulfur is stable. With 1 bond and 6 dots, each oxygen is stable. But what we didn't go over before is a concept called formal charge. Now what formal charge is, it's a comparison between how many electrons that an atom brought to this compound or ion compared to how many it now has. And so when setting this sulfate up, you would see that sulfur has, when it's neutral, 6 valence electrons. When you're counting up formal charge, each bond only counts for 1 electron. And so the sulfur here has 1, 2, 3, 4 electrons that it owns or possesses. Its normal valence is that it brought 6 electrons, but it's really only owning 4. And so its formal charge is +2. For each oxygen, they also had 6 valence electrons to bring to this polyatomic ion. And looking at how many they each have, 1, 2, 3, 4, 5, 6 electrons that they own on their own, and the 1 that they are splitting with the sulfur in this bond, the formal charge, they brought 6, but they own 7. They each have a -1 for their formal charge. Now notice that the formal charges for all the atoms here add up to the overall charge on that ion. And that is going to be true even when we fix this. But valid Lewis dot diagrams minimize the number of atoms that have formal charges. And so to minimize, we've got all these atoms have a formal charge right now, but they shouldn't. We should try to minimize that. We can fix that by taking two of these dots and turning them into a double bond. That would make the formal charge on this oxygen 0, and it would bring the formal charge on this sulfur to only +1. If we did the same thing with another oxygen, then that would mean two oxygens now would have a formal charge of 0, and the sulfur would have a formal charge of 0. It's all right that the sulfur is going to have more than 8 electrons because it has an empty d sublevel where it can put those extra electrons. And so applying this idea of formal charge, the correct Lewis dot diagram for sulfate looks like this. Where the formal charge now on the sulfur and these two oxygens is 0, the formal charge on this is still -1, and this is -1, which brings our total charge to 2-. Look at this molecule now. It's a neutrally charged molecule, and if you follow the steps, there are 2 carbons, and so it's got 2 central atoms, and they're going to end up having to be double bonded. Now with this is how it would have to be put together, and I arbitrarily for here chose the chlorines to be on the same side. Whether it's the top or the bottom, it technically is the same molecule because they could just be flipped. But the important thing is that the chlorines are on the same side. Here, the chlorines are on the opposite side. And so these are called geometric isomers, where across a double bond, things could either be on the same side or on opposite sides. And when they are on the same side, if there are two things that are similar that are on the same side, that is called a cis isomer. And if they are on different sides, that is called the trans isomer. And our last example is going to deal with this, nitrite. And before, recall that I said it was arbitrary that I chose to double bond to this oxygen instead of this one. Well, in reality, the double bond actually is flipping back and forth, and that needs to be represented somehow. That's called resonance. And so when you have an option and each option is just as good as the other, in reality it ends up being that it's a blend of all of the options put together. How that works with nitrite is like this. This was the original that I drew earlier, but an equal representation could have been the double bond on the other side. And so we would draw a double arrow showing that they're both equal representations of this thing. Ignore these. I put 2 extra electrons in, and I am writing in pen. So what this means is that these are both equally valid, and that in reality, the real structure for this would be a blend of these two, that this bond, instead of being double or single, is more like a 1.5 bond. This bond, instead of being single or double, is more like being a 1.5 bond, and those can be represented like this. And because in this diagram, the oxygen had 4 dots, and in this one it has 6, the blend would be that it has 5. Drawing your final picture like this or like this is equally correct, so long as you remember to put the charge in the brackets. So those are the different types of things that you might see that are beyond high school level that you can incorporate, whether it's formal charge and expanding the octet or having more than 8 electrons around something, whether it's looking at both forms of a geometric isomer, or whether it's correctly applying resonance. Those are ideas that are more correct than what you've learned, and you'll learn in an AP or college level course. Thanks for making it this far. We'll do plenty of practice in class. If this isn't clear, then make sure to ask your instructor, and we'll help you out in whatever way that we can with as many examples as we can.